Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. I welcome you all in class of Elementary Number Theory by David M. Burton. Our discussion is continuing on chapter number 8, Primitive Roots and Indices. In today's lecture, we will discuss the core topic of this chapter, that is the primitive roots of an integer. Lastly, we discussed concept of order of an integer. I hope you have clear understanding how to calculate the order of an integer. So now we discuss what does mean by the roots of an integer, primitive roots of an integer. Let n greater than 1 be a positive integer, and a is an integer. It will be negative or positive both, and GCD of greatest common divisor of a and n is equal to 1. Then a is called primitive root of n if its order is phi of n. In other words, if a raised to power phi of n is congruent to 1 modulo n, then a is called primitive root of integer n. So this definition is very simple. If an integer a has the order phi of n, what does mean by the phi of n? Phi of n is Euler-Tauschan function. This is the Euler-Tauschan function. Actually, this function gives the number of integers which are less than or equal to n, and they are relatively prime to n. So it gives all the number of positive integers that are less than or equal to n but are relatively primes. For example, if you calculate phi of 6 mean all those integers which are relatively prime to 6. So there are only two integers which are relatively prime to 6. First is 1 and second is 5. Because you can see here the GCD of 1 and 6 is 1, and 5 and 6 is also 1, while all other integers which are less than or equal to 6 like 2, 3, 4, all these integers are not relatively prime to 6. For example, GCD of 2 and 6, this is clearly equal to 2, not equal to 1. So 2 and 6 is not relatively prime. So there are only two integers 1 and 5 which are relatively prime to 6. So phi of 6 is equal to 2. Suppose your number is 100. So now what is the method to calculate phi of 100? There is no need to find all those integers which are less than or equal to 100 and then you will count all those integers. There is no need. We can use a formula to find the phi of 100. Firstly, remember that phi of a prime number p is simply equal to p minus 1. For example, phi of 7 means 7 minus 1, this is equal to 6. This shows that there are 6 integers which are relatively prime to 7, and these all integers are less than 7. That is, the first integer is 1, 2, 3, 4, 5 and 6. So all the integers from 1 to 6 are always relatively prime to 7. So this formula holds for any prime p. But in case if your number is composite number, then how will you calculate this number? Firstly, we will make its prime factorization. What is the prime factorization of 100? 100 prime factorization of 100 is 2 raised to power 2, 4 into 5 raised to power 2. Now 5 of 100 equal to 5 of 2 square into 5 of 5 square. Again, we will use here a formula. If you have a prime p whose power is k, then it is simply equal to p raised to power k minus p raised to power k minus 1. So applying this formula on phi, and phi is also a multiplicative function. Multiplicative function means you can separate this product, phi of 2 square into phi of 5 square. This will, now applying this formula becomes 2 square minus 2 raised to power 1 into 5 square minus 5 raised to power 1. This gives 4 minus 2, and this is equal to 25 minus 5. So this is equal to 2, and this is equal to 20, 40. So phi of 100 shows there are 40 positive integers which are relatively prime to 100. So I hope now you have a clear understanding how you can calculate the value of Euler-Torsion function at any positive integer n. Now we take a simple example of primitive root. Suppose my n is 7. Now question is that which integer is a primitive root of n is equal to 7? This is our question. If you consider a is equal to 3, then you can observe that the firstly you can observe that GCD of 3 and 7 is equal to 1. Now you have to calculate the order of 3. What is the order of 3? How will you calculate the order of 3? You will consider the successive power of 3 and note that at which power of 3 it is congruent to 1. For example, 3 raised to power 1 is simply equal to 3. 3 square, this is equal to 9. As 9 is greater than your modulo 7, so divide 9 by 7. What is the remainder? When we divide 9 by 7, this gives a remainder equal to 2. It means 9 is congruent to 2 modulo 7. Again, take 3 raised to power 3. 3 raised to power 3 means 27. Now 27 is greater than your modulo. So when you divide 27 by 7, what is the remainder? 7 3 is 21. So this gives the remainder 4 modulo 7. If you take here 3 raised to power 4, 3 raised to power 5, I am directly taking 3 square on both sides. This gives 4 square. 4 square is equal to 16. 16. Sorry, there is a mistake here. When you divide 27 by 7, this becomes 7 3 is 21 and remainder is 6 here. 6 here. Now it is okay. Now 6 square is 36. Now when you divide 36 by 7, what is the remainder? Now remainder is 1. This shows that the order of 3 is 6. Order of 3 is 6 here. Order of 3 is 6 here, which is congruent to power of 3 is 6, which is congruent to 1 modulo 7. Next, if you calculate phi of 7 here, what is phi of 7? 7 is a prime number, and add prime p, your phi calculated as p minus 1. So this is simply phi of 7 is 7 minus 1, which is equal to 6. So we can say that 3 raised to power phi of 7 is equal to congruent to 1 modulo 7. Hence 3 is a primitive root of n is equal to 7. 3 is a primitive root of n is equal to 7. So to find primitive root, first you will calculate the order of the integer. If its order is phi of n, then we will say that that integer is a primitive root of given modulo n. We take just some more examples to elaborate the concept. Okay. Suppose by n is equal to 5. My question is find all primitive roots. Find all primitive roots of n is equal to 5 if exist. First of all, we will calculate phi of 5. This is 5 is a prime number, so iteration value of 5 is 5 minus 1. This is equal to 4. This shows that there are 4 positive integers which are relatively prime to 5. Next we find all those integers, all those positive integers which are co-prime to 5. These are, the first integer is 1, second is 2, third is 3, and fourth is 4. So these are the 4 positive integers which are relatively prime to our n is equal to 5. Now out of these four, some of them will be primitive. One cannot be a primitive root because its order is always 1. 1 raised to power 1 is always equal to 1 modulo 5. So 1 cannot be a primitive root for any integer. So leave this case. Next we consider 2. Now we calculate successive power of 2. The first power of 2 raised to power 1 is 2. Second is 2 raised to power 2, that is 4. Third one is 2 raised to power 3. This is equal to 8. When you divide 8 by 5, this gives a remainder equal to 3 modulo 5. Next, take 2 raised to power 4. 2 raised to power 4 is 16, and 16, when you divide 16 by 5, your remainder is 1. This shows that order of 2 is equal to 4 at modulo 5, and 4 is actually value of phi of 5. This is equal to phi of 5. So this shows that 2 is a primitive root of 5. Next we check is 3 also a primitive root or not. Take successive power of 3. The first power of 3 is 3 raised to power 1, that is 3. 3 raised to power 2, that is 9. When you divide 9 by 5, this gives remainder 4 modulo 5. Now take its third power, that is 3 cube. 3 raised to power 3, this is equal to 27, and when you divide 27 by 5, this gives remainder 2 here. This gives remainder 2 modulo 5. And lastly, take 3 raised to power 4. 3 raised to power 4 is equal to 81, or otherwise you can multiply both of the sides by 3. This becomes 6. when you divide 6 by 5, this gives the remainder 1. So 3 raised to power 4, 81. 81, when you divide 81 by 5, this is 16 into 5, 80. Remainder is 1. So you can notice that the order of 3 is here. Order of 3 under modulo 5 is equal to 4, which is equal to 5 of 5. So this shows that 3 is also a primitive root of 5. Okay, last number. What is the last number is 4. Four raised to power 1 is 4 and 4 raised to power 2 is 16. When you divide 16 by 5, the remainder is 1. The remainder is 1 modulo 5. This shows that the order of 4 add modulo 5 is equal to 1, which is equal to 2, sorry, which is not equal to 5 of 5. So this shows that 4 is not a primitive root of 5. So this is the concept to find the primitive root of any integer. You have to just find all those integers which are relatively prime to a given integer, and then you have to find the successive power of all relatively prime integers, and check at which power of the integer, and check the order of that integer. If the order is simply equal to phi of n, then we say that integer is a primitive root of given integer. So this is the simple concept. Now I am going to share some important facts about primitive root of an integer. And these facts, I hope, inshallah, will be very beneficial for your MCQs type questions. From this example, you have observed that from this question, you can observe that a positive integer n has more than one primitive roots. For example, in this example, when n is equal to 5, 2 and 3 both are the primitive roots of n is equal to 5. Some important facts about primitive roots of given integer. The first fact is, if n is a prime number, if n is a prime integer, then it must has primitive root. For example, you have seen that in case when my n is 7 and again when our n is 5, in both cases there exists primitive root of the integers. So in case when your n is prime number, then it is guarantee that that integer has always a primitive root. The second one is an integer n greater than 1 has primitive roots if and only if it is of the form your n is equal to 2, or your n is equal to 4, or your n is equal to p raised to power q k, or it is of the form 2 into p raised to power k, where p is an odd prime, and k is greater than or equal to 1. So this is another important fact. If your integer n, whose primitive root you want to calculate, if it is 2 or 4, or it is power of any prime p, or 2 times power of prime p, where p is an odd prime, because there is only one even prime, that is 2, that is mentioned here. All other primes are odd. So for example, does there exist any primitive root of 9? Yes, because 9 can be written as 3 square, that is the form of p raised to power k. P is 3 here and k is 2 here. So this shows that this number is of the form p raised to power k, hence 9 has a primitive root. 18, because if you make the prime factorization of 18, this can be written as 2 into 3 square, that is of the form this. So this shows that this number is also has primitive root. So the natural question arises that is it possible that every integer has a primitive root? Because the fact number 1 says that the prime number always has a primitive root. In case of composite number, can you say it will always have a primitive root or not? The answer is no. Every composite number not always have a primitive root. For example, take n is equal to 8. My question is that find all the primitive root of n is equal to 8 if exist. Firstly, what is the value of phi of n here? Phi of n is simply phi of 8. Prime factorization of 8 is 2 raised to power 3. How can we calculate phi? This is the simple formula. In case of when your integer is a power of some prime p, this is equal to 2 raised to power 3 minus 2 square, 8 minus 4, this is equal to 4. So there are the 4 positive integers which are greater than 1, less than or equal to 8, and relatively prime to 8. And those integers are 1, 3, 5 and 7. These 4 integers are relatively prime to 8. Now out of these 4 integers, we have to check which integer, if possible, is a primitive root of 8 or not. So it means we have to calculate the order of these integers. Leave the case of 1, because 1 is always has the order 1. What is the order of 3? You can observe that 3 square is congruent to 1 modulo 8. 3 square 9, 9 minus 1 is 8, 8 is divisible by 8. So this shows that the order of 3 under modulo 8 is equal to 2, which is not equal to 5 of 8. So this shows that 3 is not a primitive root. 3 is not a. Now consider 5. 5 square. 5 square is 25. 25 is congruent to 1 modulo 8. This also shows that order of 5 is 2, which is not equal to 5 of 8. Next, consider the last integer 7. 7 square is equal to 49, and 49 is congruent to 1 modulo 8. It means order of 7 is also 2. So there is no integer which is primitive root of 8. So this shows that every composite integer, this shows that it is not necessary that every composite integer has a primitive root. Next. Next, I am going to discuss the very important fact of this topic, and I hope you will enjoy after learning this. For the importance of this fact, I will plot here. I am going to plot an MCQs here. Number of primitive roots. Number of primitive roots for n is equal to 100 are option A 40, option B 20, option C 80, option D 16. From the first example, you have seen that a positive integer can have more than one primitive roots. So it is natural to ask how many primitive roots of any integer can exist. So if my integer is n is equal to 100, how many primitive roots of n is equal to 100 exist here? There is no need to find phi of 100. Then all those integers which are relatively prime to 100, and then out of that integers you will find the order of that. Is a very lengthy procedure. Very simple formula that we'll use here. Number of primitive roots for any positive integer are given by phi of n. So this is the simple formula to calculate how many primitive root of any positive integer can exist. So this is equal to phi of what is n? My n is 100. So this is equal to what is phi of 100? Phi of 100 is here. This is 40. This is phi of 100. Phi of 100 is 40 here. So this becomes phi of 40. Now again we have to find the value of phi of 40. We will make the prime factorization of 40? The prime factorization of 40 is 8 into 5, that is 2 raised to power 3. 2 raised to power 3 into 5. Again, using the multiplicative property of 5, you can write it as 5 of 2 cube into 5 of 5. 5 of 2 cube means 2 cube minus 2 square. And this, what is 5 of 5? This is equal to, 5 is a prime number. So we can use directly this formula. This is p minus 1. So 5 minus 1 here. And this is equal to 8 minus 4 into 4. And this is equal to finally 16. It means option D is correct here. So this shows that there are 16's primitive root of integer n is equal to 100. Lastly, I am going to discuss another criteria to check whether the given integer has a primitive root and which integer is a primitive root for a given integer. There is no need to find all the successive power of all those integers which are relatively prime to given integer. So what is the another criteria? Another criteria to check to find primitive roots of given integer. Let n is greater than 1, a is integer, GCD of a and n is equal to 1. Let phi of n is equal to m. We suppose y of n is equal to m here. Then to check, then to find the primitive root of integer n, we can use the following step. Step number 1. Find all those integers which are relatively prime to or co-prime to n. This will be our first step. The second step, this is important. Only those integers a calculated in step number 1 will be primitive roots that satisfy a raised to power m over q not congruent to 1 modulo n. What is q? Where q is a prime divisor of n, of m. N means phi of n. Next, I elaborate the criteria by a simple example. Okay. Take n is equal to 9. Question is, find all the primitive root of n is equal to 9. Simply, firstly we calculate phi of n. What is phi of n? Phi of 9 is equal to phi of 3 square. 3 square mean 3 square minus 3 raised to the power 1. 9 minus 3, this is equal to 6. So there are the 6 positive integers which are relatively prime to 9. And these numbers are 1, 2, 4, 5, 7, 8. 1, 2, 3, 4, 5, 6. So these 6 are relatively prime to 9. Now out of these 6, we have to find all those integers which could be primitive root of 9. There is no need to check 1. Next, start from 2. There is no need to check all the successive power of 2. You have to check only those powers which are in the prime factorization of 6. This is 2 into 3. So you have to take only these two power, 2 and 3. Otherwise, put here our age 2 here. What is m? M mean this is phi of 9, which is equal to phi of n. This is equal to m. My m is 6. Q mean a prime divisor of 6. The first prime divisor is 2. This is equal to 2. This becomes 2 raised to power 3. And when you take Q other prime, that is 3, this power become 2 square. So there is so you have to check only these two powers. So this becomes 2 raised to power 3. What is 2 raised to power 3? This is equal to 8. And 8 is not congruent to 9. Similarly, when you consider 2 square is equal to 4, and this is also not congruent to 1, sorry, not congruent to 1. Not congruent to 1. Modulo 9, not congruent to 1. Modulo 9. Because both power of 2, which are the prime factorization of 6 mean phi of n, are not congruent to 1. This shows that 2 is a primitive root of 9. So this is very simple criteria. Suppose next we check 4. Take the first power, that is 4 square. 4 square is equal to 16. When you divide 16 by 9, the remainder is 7. So this is not congruent to 1 modulo 9. Okay. Next take other power. This is 4 cube. 4 cube is 64. Now when you divide 64 by 9, this becomes 9 7 is 63. Your remainder is 1. Now your 64 is congruent to 1 modulo 9. This shows that 4 does not qualify the area, this result, because this is congruent to 1. In other words, you can say that the order of 4 congruent 9, modulo 9 is equal to 3, which is not equal to phi of n. So 4 is not a primitive root of 9. One more, suppose we take 7. your 7 square. 7 square is 49, and when you divide 49 by 9, this is equal to 9 5s are 45, remainder is 4. Remainder is 4. This is not congruent to 1. Now take other power. 7 cube. 7 cube means multiply on both sides by 7 on both sides. When you multiply by 7 here, this becomes 7 cube, and this becomes 28. And 28 is greater than 9, so we will divide 28 by 9. The remainder is 1 here. Remainder is 1 here. Remainder is 1. When you divide 28 by 9, the remainder is 1. This shows that 7 cube is congruent to 1. It means 7 is not a primitive root of 9. If you check 5 raised to power 2, this is 25. When you divide 25 by 9, this becomes 9 to the 18. This is 7, not congruent to 1. 5 cube, multiply on both sides by 5, this becomes 5 7 the 35. 35, when you divide 35 by 9, this becomes 35 by 9. 9 3s are 20, 9 4s are 36, and 9 3s are 27. Remainder is 8. That is not congruent to 1. Modulo 9. This shows that 5 is another primitive root of 9. So I hope after this long discussion, now you have a clear understanding about the primitive root of an integer, how we can define it, how can we calculate, how can, if we have a given number and directly we have to check whether the given integer is a primitive or not, you can use this criteria. This is very simple. There is no need to find all the successive power of that integer. There is no need to apply the proper definition of primitive root. So if you find this lecture helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.